This first problem is the revenue problem like we did in class. It's not really different. The revenue you make from selling something is the number of things you sell times the price you sell them for. So that's not all that complicated. We need to turn this into a function with just one variable. And in the problem, they tell us that the one variable here should be x. We don't really have to make any guesses about it. So instead of x times p, I'm going to use x times what p is equal to. This expression up here tells me that price is always given by x times, by 21 minus 1/10 x. So my revenue function so a function with just one variable input, the x, will be given by this expression. The domain of this, well, the domain just has to do with trying to make sort of sense-making of the variables. X has to be at least 0 because x stands for the number of things that are demanded, so it doesn't make any sense for the demand to be negative. And also the price should be not negative. Having a negative price is something we don't want to consider, so we want price to be at least 0. The easiest way to find out when this happens, obviously this is already in terms of x, so we don't have to do anything to that. That's going to be in the right form. This one, though, we really want this as a limitation on x, not on p. And so what we need to do is just first figure out when p is equal to 0, and then use that to reason out when p is greater than or equal to 0. So solving p equals 0 is just a matter of setting the expression for p equal to 0, and we'll find that that happens when x is 210. So at 210 for x, there's a breaking point for p. Price is 0 at that point. If you look at the equation, a little bit higher values of x will make price negative, and lower values of x will keep price positive. So price stays at least 0. So this condition is met when x is less than or equal to 210. So the two conditions I have are that x needs to be at least 0, and x can be no more than 210, the latter because that would drive the price to be negative. So as an interval, we would write that as 0, 210 with square brackets to indicate that 0 and 210 are included. The value of x that will maximize revenue, we're using in a big way here that revenue is a quadratic function. So we know revenue is a function, since it's quadratic, it's going to have this parabola shape, and of course the maximum value of revenue will be at the high points. What I'm really trying to find here is the vertex of this parabola. What we learned about this was that if you have this in its factored form, then the easiest thing to do is to use the factored form to find the intercepts. And if you found the intercepts, then the vertex is halfway in between. If this r of x expression that we're starting with was not factored, then it wouldn't make any sense to have to go through a lot of work to factor it just to find the vertex. That's when I'd want to use my minus b over 2a formula for the equicoordinate of the intercept. But if it's factored, there's no reason to multiply it out. So we can see that one of the intercepts is going to be 0, 0, because when x equals 0, the entire expression here is equal to 0. So this being 0 makes the whole thing 0. Also, this being 0 makes the whole thing 0. So 21 minus 1/10 x was 0. Remember, we already did that. That actually happened. So this term, this factor, is 0 when x is 210. So we know that another x-intercept of this thing is 210, 0. And you can check that. You can plug r of 0. You plug 0 in for x, and you'll get 0. You can put 210 in for x, and check, and sure enough, you'll get 0. So those are not things you have to just guess at. You can actually check them. And so therefore the vertex is happening halfway in between. So at 105, for the x-coordinate, I'll have the vertex of this parabola. Finding the y-coordinate would tell me what that revenue is, but the question never asks that. So I'll just answer the question that was asked. So revenue is maximized if x is 105. So in other words, selling 105 objects will give you the most revenue that you can get. If you sell more than that, your price will have gone down enough that you actually will be making less money from selling more than 105. So the price that creates this much demand, this is just a matter of going back to the price equation up here. It's asking about price, so I just have to find where price occurs in the problem. Price is 21 minus 1/10 x. The x here is 105. So I have 21 minus 105 over 10. So 21 minus 10.5 is 10.5. So if I set a price for whatever this is I'm selling at $10.50 each, the theory says that that will create a demand, according to this equation, will create demand for 105 objects. And when we sell 105 objects, then the revenue is at its maximum. So in problem 2, we're working with tossing the ball in the air. So the fact that the ball takes 6 seconds from when it's released to be back when it to come down again means that if we think of 0 feet as the point where I'm releasing the ball at time 0, then the piece of information I'm given here is that when you put 6 seconds in for time, you also get 0 feet. So it's back down to the point where you let it go after 6 seconds. The second thing can be used to our advantage, though, because we also can find h of 6 by plugging 6 in for t in this equation. So according to the equation, h of 6 is 6 times v. I'm going to rewrite v, instead of writing v times 6, it's a little awkward, minus 16 times 6 squared. So 6 squared is 36, so I'm just going to squeeze that in there. No, I'm not. So 16 times 36. So in order for this to be 0, in order for 16v minus 16 times 36 to equal 0, that will mean that, oops, not 16v, sorry, 6v, means that 6v will have to be equal to 16 times 36, and so if I divide both sides by 6, I'll get v as 96. So this is 96 feet per second. This is a speed. So this is the amount. This is the speed that I throw the ball up in the air. I suggested converting this to miles per hour just so you could see if this was a reasonable speed. Is this like the speed of a car, the speed of a Little League pitcher, the speed of a Major League pitcher, or faster than anybody could possibly throw a ball? So I'll leave that to you. That's not something that I would ever put on a test because I don't know that you'd remember the conversion factors. But using the fact that there are 3,600 seconds in an hour and 5,280 feet in a mile, you should be able to do that. So how high does the ball go? Well, keep in mind that now I actually know the formula without parameters in it. I now know this. The formula that I have up here is really 96t minus 16t squared. So I don't have to have the v in there anymore. And this is not in a factored form already. It's not hard to factor, but it's not in a factored form already. So to find the vertex of this parabola, in this case, I will use my minus b over 2a formula. So minus 96 over minus negative 16. So minus 32. And so that's at the 3-second mark. So that's not too surprising, right? If it took 6 seconds to come down, you figure it's at its highest point at the halfway point because the movement should be symmetric. How high is it at that point? That's just h of 3. And again, using the real formula that I have here, that's 96 times 3 minus 16 times 3 squared, which I believe is 144 feet.